Good afternoon, mechanical engineering students. I apologize. I will not be visible during this lecture. Uh, there is a problem with the camera in my laptop. So today we'll be discussing electrochemistry, which is an essential topic that connects chemistry with engineering applications. So in this lesson, we'll explore how electrical energy can drive chemical reactions and how these reactions, in turn, power the technologies we use in terms of materials processing, corrosion prevention, batteries, and even manufacturing systems. So here are the outlines for this topic. So when you say about electrochemistry, when you say about electrochemistry, it is a study of how chemical reactions produce or use electrical energy through redox reaction or reduction oxidation processes. So this electrochemistry involves galvanic cells and electrolysis. So when you say galvanic cells, these are the ones who generate current. And when we say electrolysis, these are the ones who use current to drive reactions. So how important is electrochemistry to mechanical engineering? So first is it helps in corrosion control, wherein materials materials failure prevent it prevents materials failure and extends equipment life. So another thing is it is important in batteries and fuel cells. So the power systems for vehicles and tools. And another is the surface treatment, wherein it involves electroplating and coating for durability of the material. Then sustainability. So it will supports efficient, long-lasting of designs of the equipment. So this electrochemistry builds understanding uh, to design safer, more efficient, and durable systems. So here are the learning outcomes for the topic on electrochemistry. So let's start with the foundation of modern mechanical engineering and manufacturing. So here in this manufacturing process, coke, pellets, limestone, iron ore are converted into strong, versatile materials for machines, vehicles, and structures. So understanding stage here in the each stage in this manufacturing aids in material selection and performance analysis. So first is in the process we have the iron making. So in the iron making, it involves smelting iron ore, coke, and limestone in a blast furnace to produce molten iron or hot material. Then another the next stage is the steel making. So we're in basic oxygen furnace. In it involves basic oxygen furnace or BOF and electric arc furnace EAF. So in the BOF, it refines hot metal using oxygen to lower carbon, while in the EAF, it melts scrap steel using electric power, wherein energy efficient and recyclable. So next is the continuous coating. So in the no continuous casting. So in the continuous casting, uh, it converts molten steel to billets, blooms, and slab. So next step is the rolling or forming. So in here, hot or cold rolling, hot or cold rolling shapes metal into plates, into sheets, into bars or wires. So it, this processes as shown here because this is the basis for designing high strength, durable, corrosion resistant materials. So this supports the material selection, cost control, and failure analysis in mechanical systems. So what do you think happens when strong shiny steel is left outside under rain and air for months? And why does it turn into this reddish, flaky material? So, what process do you call this? This process is called corrosion, a natural electrochemical reaction that deteriorates metals. So, corrosion is one of the most common and costly problems in engineering. It happens when metals gradually return to their more stable oxide formed through electrochemical reactions. In other words, the metal that once came from ore is trying to go back to becoming ore again. So, as mechanical engineers, understanding corrosion is essential. It is not just to recognize why materials fail, but to design systems, design machines, and structures that can withstand the harsh environments they operate in. So let's look deeper into how corrosion happens and the science behind it. So corrosion is defined as the gradual deterioration of metals due to chemical or electrochemical reactions with the environment, often involving oxygen and moisture. It weakens structures, reduces efficiency, and shortens equipment life, lifespan. So there are types of corrosion. First is we have the uniform corrosion, wherein it occurs evenly over large areas, typically rusting of steel in air and moisture. Another type of corrosion is galvanic corrosion. It happens when two dissimilar metals contact through an electrolyte. So one corrodes faster compared with the other metal. So the third type of corrosion is the crevice corrosion, wherein it forms in tight gaps or joints where stagnant solution promotes localized attack. So understanding corrosion helps engineers prevent material failure, choose proper alloys, and design longer lasting systems. So corrosion appears in different forms depending on exposure and material conditions. So in here on the left side, the rusted chain uniforms shows uniform corrosion, wherein the entire surface is attacked evenly over time due to exposure to air and sea water. So on the right side here, the grill cover, the grill cover here shows crevice corrosion forming around the tight joint where the handle meets the surface, wherein moisture and ions get trapped in the gums, accelerating localized corrosion. These examples highlight how environment and geometry influence corrosion behavior in real engineering structures. Now that we've seen how corrosion looks in practice, let's explore the electrochemical reactions that make this process possible. This process possible, which we call oxidation and reduction processes. So this diagram illustrates the galvanic series chart. So the galvanic series ranks metals by their tendency to corrode in an electrolyte such as sea water. So metals at the top here, the metals at the top, such as magnesium, zinc, galvanized steel, aluminum, mild steel, are more active compared, are more active. It means they are more active. It means they corrode easily and act as the anode. So however, the metals here below at the bottom, such as gold, graphite, platinum, titanium, silver, stainless steel 316304, are more noble. They resist corrosion and act as the cathode. So when two dissimilar metals are connected, the anodic, uh, the anodic, the anodic, which is the active metal, corrodes first, compared with the uh, cathodic or noble metals. So this galvanic series chart used to predict the galvanic corrosion when different metals are joined. So this guides material selection in design, such as avoid pairing aluminum with copper in humid or marine environments. So this is the basis for sacrificial protection systems such as zinc coated galvanized steel. So not all metals corrode the same way. Their corrosion behavior depends on how stable their oxide layers are, such as this aluminum. Aluminum corrodes faster in theory. If you look at the table, let's go back to the table. Here, aluminum oxide, aluminum corrodes faster in theory compared with iron. However, however, aluminum oxide layer that forms that forms is thin, thin, compact, and protective. So preventing further damage. That's why aluminum corrodes faster, uh, does not corrodes faster compared to iron. But in theory, it corrodes faster, but in reality, it doesn't corrode faster compared to iron because aluminum oxide layer, as you can see in the figure, the aluminum oxide layer that forms is thin, compact, and protective, which prevents further damage. Unlike iron, on the other hand, usually iron forms iron oxide, just like here in this picture. Here forms iron oxide, which we call rust, that flakes off, continuously exposing new metal to air and moisture, making corrosion progressive. This difference explains why aluminum structures last longer outdoors than unprotected steel. So even though aluminum is more reactive, its protective oxide layer makes it more durable. So unlike iron, if you compare it with iron, as I've mentioned. So let's connect this behavior to electrochemical principles and oxidation, reduction reactions. So before metals like iron can form oxides, which is rust, specific conditions must exist. So it depends on the moisture, it depends on the oxygen and ions. So rusting is slow. So usually we study faster electrochemical reactions to understand how corrosion occurs. So in the redox reaction or oxygen oxygen reactions, it involves the transfer of electrons between substances. So when you say redox, when you say oxidation, it refers to the loss of electrons. So it means metal atoms become ions. When you say reduction, it means gain of electrons. It means ions or oxygen are reduced. So this paired reaction explains how corrosion and galvanic cells work. For example, here, in resting, like iron is oxidized. It means iron is oxidized. It forms into, it means iron is oxidized. It means it forms into F2 plus, 2 electrons of iron. While oxygen is reduced, it means oxygen is reduced to form hydroxide ion. Form into hydroxide ions. So therefore, every corrosion process is an electrochemical reaction in disguise. So understanding oxidation and reduction helps engineers predict corrosion sites and develop protection methods, such as coatings or sacrificial anodes. In every oxidation, reduction, or redox reaction, one substance loses electrons. So when you say loses electrons, it means oxidation. While another gains electrons, it means reduction. These two processes always occur together. So oxidation cannot happen without a corresponding reduction. So example, if you have an example here, copper and silver nitrate reaction. So when copper wire is placed in silver nitrate solution, a redox reaction occurs. So here, if you have an example here, copper and silver nitrate reaction, so the oxidation is at copper. So oxidation here is at copper, wherein the copper solid copper, will form into copper ions in chaos solution plus the 2 electrons. When you say in this example also, the reduction here is the silver. So reduction, as I've mentioned, the reduction here is the silver. So it means you have here silver ion in chaos solution plus the 2 electrons will form into silver solid. So however, this is not balanced, so you put 2 here, and this one is 2. Because there are 2 electrons, so it means you have also to put here in order there will be 2. It will be balanced. So the color change in the solution and silver crystals forming on copper confirm that electron transfer has occurred. So these have reactions to illustrate how galvanic cells and corrosion work at the microscopic level. So we're in one part oxidizes here, the copper, while the other part, the silver, reduces. So understanding this helps engineers design, again, materials and prevent unwanted electrochemical reactions in real systems. So let me explain this clearly through an illustration. So this experiment shows this experiment shows what happens when a copper wire is immersed in a silver nitrate solution. So at first here in image A, the solution is colorless and the copper surface is clean and shiny. So after a short time in this image 2 B, the solution starts to turn blue. So this tells us that copper ions are forming as copper begins to oxidize. Then later in image C, we can see here already the silver crystals forming on the copper wire. This come from silver ions in the solution being reduced to solid silver. Here are the solid silver. So this simple setup already demonstrates both oxidation and reduction happening at the same time. So a redox reaction in action here. This the figure illustrates already a redox reaction in action. So now that we know what we can see, let's look at what's happening at the atomic level, how these ions and electrons are moving. So as I've mentioned on the previous slide, the blue color tells us that copper ions are in the solution. So meaning the copper atoms on the wire are losing 2 electrons. This process is called oxidation. So the copper metal here, the solid copper or copper metal, turns into copper ions, and the electrons that it loses that it loses do not disappear. So they move to these ions move to silver ions in the solution. So the point here is that each silver ion takes one of those electrons and becomes solid silver metal. And that's what we call here the reduction. So that's why silver silver crystals appear on the copper wire. The silver ions here are reduced and the copper here are oxidized. So the color change and crystal formation are visual proof of the electron exchange, as you can see here. So here are already silver on the copper ions, on the copper. So, but here's something interesting here. Copper losses, here the copper losses 2 electrons, while each silver, now the silver ion gains 1 electron. So how do we make sure that the reaction stays balanced? So let's find out on our next slide. So how do you balance this one? So to keep the reaction balanced, we need two silver ions to gain the 2 electrons that one copper atom losses. So when we multiply the silver half reaction by 2, and the number of electrons transferred on both sides becomes equal. So now everything here is already balanced. So 2 electrons lost here in the copper, and there are 2 electrons gained here in the silver. So this shows that in every redox reaction or oxidation reduction reaction, this reaction always occur together, and in equal measure. So from a simple color and silver deposit, uh, we have revealed that the fundamental process behind corrosion, electroplating, and even how batteries work, the control, it is the controlled movement of electrons. So when we combine these two half reactions, the electrons cancel here, the electrons cancel. It means the electrons here cancel. Because the number of electrons lost equals, the number of electrons lost is equal to the number of electrons gained here. So this is the ionic equation for the redox reactions. So it tells us here that the overall chemical change wherein copper metal is oxidized to form copper ions, and the silver ions are reduced to form into silver metal. So now that if we could separate these two reactions, oxidation and reduction, into two different containers and force electrons to travel through a wire, that's exactly what happens in galvanic cell. So in any redox reaction, the substance that loses electrons, in this case is the copper. In this case is the copper, but by giving away electrons, it causes the silver to be reduced. So the copper here is the reducing agent. On the other hand, the species that gains electrons here is the silver ion, which is the oxidizing agent. So silver ions are reduced, but by accepting electrons, they cause copper to oxidize. So the silver ions is the oxidizing agent. Now that we know who the oxidizing and reducing agents are, let's see how we can separate their reactions and make the electrons travel through a wire producing electricity. So in a galvanic cell, we separate the oxidation and reduction half reactions into two different containers called half cells. So electrons flow through a wire from the reducing agent, the metal that gets the oxidized, and to the oxidizing agent, the ions that get reduced. So to complete the circuit, ions must also flow. That's where the salt bridge comes in. So let's see how this works, our copper silver system. So if we use a salt bridge made of ammonium chloride, this one, the ammonium chloride, the ammonium chloride, in here, the ammonium ions migrate to the silver half cell to replace the lost silver ions. So the chloride ions here, the chloride ions move to the copper half cell to balance the newly formed copper ions. So this keeps the charge in both beakers neutral and allows the electron flow to continue. Now let's visualize this in the full step. So in here, this diagram illustrates the completed galvanic cell. So on the left side here, on this left side, when the copper and silver half cells are connected by a wire, no current flows. It means when they are connected by a wire, there no current flows these two uh between these two between these two half cells. So so it so the voltmeter here reads 0.00 volt because the circuit is incomplete here. The circuit is incomplete here because there is no salt bridge. So it needs a salt bridge in order uh in in order the in order the circuit to be complete. So here on letter B on the right side, when the salt bridge is connected, is connected, ions can now move between. It means ions can now move between the half cells. So completing the circuit. So the voltmeter now reads 0.46 volts, meaning electrons are here, electrons are already flowing or are already moving from the copper electrode, which is the anode, to the silver electrode, which is the cathode. That's the working principle. This shows the working principle of a galvanic cell. So a redox reaction generates an electric current. So to summarize, the copper silver reaction shows oxidation and reduction happening together. So copper here acts as a reducing agent, which is the which is the which is the anode, while the while the while the silver ions acts as the oxidizing agent. So separating the half reactions allows allows electrons to flow through a wire. So the salt bridge maintains electrical neutrality, uh, enabling continuous current flow. So without the salt bridge, the it doesn't work. So there is no transfer of from an electron to another electron. To an electron of in one metal to another metal. So this is the foundation of how batteries work. So it controlled redox reaction that convert chemical energy into electrical energy. Now, we've seen how the galvanic cell works. Let's define the key terms here. So what are the key terms that we should consider? So first is the electrodes. So what do you mean by electrodes? Electrodes are the conducting sites where oxidation or reduction takes place. So the electrode where oxidation occurs is the anode. The electrode where reduction occurs is the cathode. So remember this. So when you say anode, it means oxidation. When you say reduction, it means cathode. So just remember anox, red cut. So it means anox, it means anode. Oxidation happens. Reduction, it means red cut, it means reduction will happen in the cathode. So Remember, an anox oxidation occurs at the anode, and the red dot reduction occurs at the cathode. So next, we introduce something new, the cell notation. What do you mean by this cell notation? The cell notation is a shorthand way to represent the entire electrochemical cell. So let's electrochemical cells. So cell notation lists the metals and ions involved in the reaction. So a vertical line here, a single vertical line denotes a phase boundary. So it means liquid, solid. It means the phases of this, the phases uh, of these ions, or the phases of these ions, or the phases of these, the phases of these ions, or or chemical. So a double vertical line here denotes a salt bridge. So the anode is written, the anode is written on the left here, while the cathode is on the right. So next we introduce something new. Next is we will look at what this notation looks like and how we can write one for the copper silver cell we just discussed. So the cell notation summarizes what's happening in the galvanic cell. So the general format here is each vertical line means a phase boundary, while the double line represents the salt bridge. So for copper silver cell, the notation is you have here copper solid, then you have the phase boundary, wherein you have here the copper ions in the aqueous solution, 1 molarity. Then you have the double here. It means there's a salt bridge here. So a salt bridge. Then you have here the silver ion in aqueous solution in 1 molarity. And then again, this one, there's another single vertical line wherein there's a phase boundary between the silver ions and the silver solid. So remember that in here you have the anode, you have the phase boundary, the electrolyte of anode, the salt bridge, the electrolyte of the cathode, the phase boundary, and the cathode. So notice that the anode here is always written on the left, while the cathode is written on the right. So when the solutions, what do you mean by this one? When the solutions are 1M, 1 molarity, and 1 molarity, or gases, if there is, if it involves gases also, it is this 1 molarity is at 1 atmosphere, which we call the standard state of the electrochemical cell. So now that we can write up a shorthand for the cell, let's look more closely at what's happening inside the cell down to the atomic level. So at the atomic level, before the two half cells are connected by the salt bridge, small charge build-ups occur at the interface between each electrode and its solution. So at the anode, oxidation happens. So copper atoms lost the electrons and entered the solution as copper ions. So leaving the electrode with a negative charge. So at the cathode, reduction happens. So it means that the silver ions silver ions in the solution gain electrons and deposit as silver metal, leaving a positive charge on the cathode. So these charge imbalances create a tiny potential difference. But without a salt bridge, the system cannot stay neutral. So let's visualize this. Uh, what happens when we don't yet have a salt bridge to balance to those charges? So here's a clear picture. Here's a clear picture here. So on this one on the left, you see that the copper electrode producing copper ions, making the solution more positive and electrode more negative. So on the right, silver ions are being reduced to silver metals. So leaving behind an excess of negative ions in solution. So without the salt without a salt bridge, this change imbalances quickly stop the reactions. So that's why the voltmeter here reads 0.00 volts, meaning no current flows. That's why the salt bridge is essential. It allows ions to migrate between half cells and maintain charge balance so the reaction can continue. Now that we understand how galvanic cells work, let's apply the same principle to something we encounter in everyday life, just like the metal corrosion. So from redox reactions to galvanic cells and even corrosion, the same core principle applies. The movement of electrons from one material to another. So when metals touch a solution, oxidation and reduction can be key even without us applying electrolysis. So if the solution contains ions that can be reduced, the reaction starts to flow and the corrosion begins. So when two different metals are in contact, like tin and steel in a tin can, one metal acts as the anode, wherein it loses electrons and corrodes, while the other becomes the anode. It means that it gains electrons and is protected. So this paired reaction is what we call the galvanic corrosion. So it's basically a tiny battery forming on a metal surface. So here we can see what happens in real life. So the tin coating on a can protects the steel underneath, as long as protects steel, the steel underneath the under underneath underneath as long as it's an as long as it's unbroken. So one scratch, my scratch to metal, the tin metal, the ex, uh the exposed iron becomes the anode and it starts to corrode rapidly, as you can see here in the brown color. So the tin stays intact here as the cathode, but that accelerates the rusting of the exposed ions. This is why food cans rust from the inside when scratched. It's a perfect example of galvanic corrosion in action. So corrosion does not always need two different metals. two different metals. So even one metal like here, for example, iron can corrode uniformly when it reacts with oxygen dissolved in water. In this process, the irons, the iron metal, the iron metal acts as both electrodes here. The iron metal, both electrodes as cathode and anode. So at the anode, the iron here, the iron oxidizes, the iron oxidizes into the iron oxidizes uh the iron oxidizes into iron ions. Then at the cathode here, the oxygen is reduced to form water or hydrogen, ions. So salt in the environment speeds this up because it releases conductivity. This is why or reinforcing bars rust inside concrete. The oxygen and water create electrochemical cells on the same piece of metal. So to measure how strongly one metal tends to corrode or react, we use cell potential. So this is like the voltage that pushes electrons through a wire. So a voltmeter helps helps us measure the potential difference between two electrodes. So the negative side indicates the cathode. Uh, the negative side indicates the anode, where oxidation happens, and the positive side indicates the cathode, where reduction happens. So in every redox reaction or oxidation reduction reaction has its own fixed polarity and voltage. So it tells us the direction the electrons naturally flows. Now let's apply that concept. So when we connect copper and silver half cells, we measure 0.462 volts. So copper and iron will give 0.434, while iron and silver will give 0.028. So when you add the last two, you get the last first exactly. So 0.434 plus 0.028 is equal to 0.462 volts. So that means that the cell potentials behave like state functions. So this is similar to energy. The total does not depend on the path, only on the starting and ending electrodes. That's why the cell potentials behave like state functions. So this consistency allows scientists to build a compare scale of standard cell potentials. So here is a visual of those three experiments. As I've mentioned, each pair half cells produces a characteristic potential. So for copper and iron, it produces 0.43 volts, while iron and silver, it produces 0.03 volts, and copper and silver, it produces 0.46 volts. Have you noticed that how the sum rule we mentioned is clearly shown? So this process tells us that every electrode pair has its own fixed potential that it can be compared to others. So to compare between metals fairly, we need a standard reference. That's where the standard hydrogen electrode, or we call it SHE, comes in. It is made of platinum immersed in 1 molar of hydrogen chloride or hydrochloric acid with hydrogen gas bubble at 1 atmosphere pressure. This step always has an assigned protocol of 0.00 volts. We measure all other half cells, relieving uh, half cells relative to this electrode. So when we say copper has plus 0.34 volts, it means copper is 0.34 volts more positive than hydrogen under positive conditions. So here's how we write it formally. So the half cell notation is you have here uh, platinum solid, and then you have here the phase change, hydrogen gas at 1 atmosphere. Then you have here the phase change of hydrogen ions, in which it is also in 1 molarity. So because the SHE is assigned 0 volts, any measured voltage when another electrode is connected reflects that other electrode's tendency to be oxidized or reduced. So depending on what metal we connect, the She can act as either the anode or the cathode. So if the metal is more reactive than hydrogen, hydrogen becomes the cathode, and the metal is oxidized uh, as oxidized. Uh, I mean the hyd the met I mean the metal is oxidized, which acts as the cathode. So if the metal is more reactive than hydrogen, hydrogen becomes the cathode, and the metal is oxidized, which acts as the anode. So if the metal is less reactive, the hydrogen gets oxidized instead. So when the anode is connected to the positive terminal of the voltmeter, the reading is negative. When the cathode is connected with the reading connected, the reading is positive. So this tells us which side is losing or gaining electrons. So finally, here's how to interpret what the sign of the potential means. So it means that a negative potential means that the She is acting as the anode, while the hydrogen is being oxidized to hydrogen ions. So a positive potential means that the She is the cathode. So the hydrogen ions are being reduced to hydrogen gas. In short, it tells us the direction of electron flow, and that's the foundation of the electrochemical uh, cell analysis. So here, The diagram shows how polarity works in galvanic cell. Just like in a regular battery, when we connect copper and silver, electrons always flow from the anode to the cathode through the external circuit. So the direction of electron flow never changes, never changes, even if we reverse the voltmeter wires. What changes is just the sign of the voltage, just like here in the illustration. So the direction of electron flow never changes, as I've mentioned, even if we reverse the voltmeter wires. What changes is the sign. It's only if you reverse this one, what changes is only the sign of the voltage reading on the meter. So on the left setup, the voltmeter's positive terminal red wire is connected to the silver electrode, which is the cathode, and the meter here reads plus 0.46 volts because electrons flow from copper to silver. That's the spontaneous direction of the redox reaction. So here in the right setup, it is simply reversed. It is simply reversed. Now that the positive terminal reverse the voltmeter connections. So now the positive terminal is connected to the copper, positive terminal to the copper, which is the anode, and instead of the silver. So the voltmeter here shows negative 0.46 volts. So notice that the direction of the electron here, then notice that the direction of the electron here, flow between the electrodes has not changed. Only the sign of the reading flip. So this shows that cell polarity is fixed by chemistry, not by how we connect the wires. Even though the measured sign can change depending on voltmeter orientation, the chemical reaction remain the same. Electrons always travel from anode to cathode. So in electrochemistry, every half cell has its own potential. So it means that a measure of how easily it gains or loses electrons. So to compare these values, scientists agreed to write all the half cell potentials as reductions, meaning each reaction is written in the form of gaining electrons. So we then measure each half cell's potential relative to a reference electrode called the standard reduction potentials or standard hydrogen electrode, or we call it SHE, which is assigned a potential of exactly 0.00 volts. All measurements are made under standard conditions. It means at standard conditions, 1 molarity concentration for aqueous ions and 1 atmospheric pressure for gases. So this ensures every experiment can be compared under the same reference frame. So now I'd like to ask you, why do you think scientists choose hydrogen as the reference electrode? So let's think about it. Why do you think scientists choose hydrogen as the reference electrode? Now, to answer that question, hydrogen was chosen as the reference because it is simple, reversible, stable, and reproducible. So reproducible. So it serves as a universal 0 point. So scientists defined its potential as exactly 0.0000 volts under standard conditions. So this provides a universal baseline. All other electrodes potentials are measured relative to this zero. So it gives a common starting point so that everyone in the world measures cell potentials on the same scale. So this table lists the several half reactions under standard reduction potentials. So for example, here you have zinc ions plus 2 electrons will form into zinc solid. So it has a negative value, which is negative 0.763 volts, meaning zinc ions do not easily gain electrons. So they prefer to lose them, making zinc a good reducing agent. While silver here, if you look at the silver here silver ion plus 1 electron will form into silver solid or silver metal, has a positive value, which is positive 0.7794 volts, meaning that the silver ions easily gain electrons. So it means that they are good oxidizing agents. The hydrogen electrode here, by convention, is set to 0.00 volt to serve as the reference point, as I've explained earlier in the previous slide. So the higher, it means the higher, more positive the potential, the stronger the tendency to be reduced. So remember that the higher or more positive the potential, the stronger the tendency to be reduced. So even though all reactions are listed as reductions, every electrochemical cell must include one oxidation and one reduction half cell. When a half reaction is reversed to represent oxidation, the sign of its potential is also reversed. So if the reduction potential is plus 0.34 volt, the oxidation potential becomes negative 0.34 volts. So it means that if the if the reduction potential, if the reduction potential is equal to plus 0.3 volts, it means that the oxidation potential is equal to negative 0.34 volts. So some elements naturally have positive potentials, easy to reduce, while others have negative potentials, harder to reduce, but easier to oxidize. So now let's have an example on this. So let's have an example. So let me have an example here. So let's have an example. So I'll have okay, let me have a new slide here. Okay, now an example here is if you have here copper ion and copper metal, which has plus 0.337 volts, while zinc ion and zinc metal solid has negative 0.763 volts. Which one acts as the anode in galvanic cell? How do we identify which acts as the anode in a galvanic cell? So step one, let's recall what the anode and cathode do. So when you say anode, where oxidation occurs, it means the electrons are lost. Cathode, where reduction occurs, electrons are gained. So in a galvanic cell, electrons always flow from the anode to the cathode. So in a galvanic cell, remember that electrons flows from the anode to the cathode. So let's compare their standard reduction potential. So if we're given here for the copper ions and copper metal, plus 0.337 volts, and for the zinc ions and zinc metal, which is equal to negative 0.763 volts, these values show how easily each ion gains electrons. So a more positive potential, remember that a more positive potential, as I've mentioned earlier, that a more positive potential means greater tendency to be reduced. So a more negative potential means less tendency to be reduced. So now in here, we will be able to determine, we will be able to determine uh, we will be able to determine which one is reduced and which one is oxidized. So now here we it means that, as I've mentioned, that a more positive potential means greater tendency to be reduced. So it means that copper ion is reduced. It means here copper ion is reduced to copper metal, which we're in. This one is the cathode. So we'll be able to identify which one is the cathode now. So now, while the zinc here, it means the zinc ions has a lower or more negative. So it means the zinc here metal is oxidized to zinc ions. It means that here the zinc is the anode. So what happens in each half cell? So what happens in each half cell based on this based on this given. So what happens? So at the anode, the oxidation here, let me have another slide. It means in the anode here for the zinc, it means that the anode here is at the anode, at the, sorry, I'll erase again. So at the anode, wherein oxidation happens, the zinc metal will form into zinc ions, and it will gain two electrons. While the cathode here, the reduction, it may the copper ions will lose 2 electrons to form into copper metal. So here, solid, this one is also. Okay, so it means that the anode is the zinc, wherein the oxidation is negative 0.763 volts, while the cathode here is the copper, a reduction of plus 0.337 volts. So electrons flow, it means electrons flow from zinc to copper. Okay, zinc to copper. Now, let's proceed here. So let's proceed. So all potentials are measured using the She connected to the negative terminal of the voltmeter. So if the measured voltage is positive, if the measured voltage is positive, electrons flow from sheet to the other electrode, meaning the other electrode is the cathode. With that, a reduction site happens. If the measured voltage is negative, electrons flow towards She, meaning She acts as the cathode and the other electrode is the anode, or it means the oxidation site. So a positive standard reduction potential means the reduction occurs spontaneously. A negative one means oxidation is more favorable. So this is how we determine which electrode acts as anode or cathode without directly measuring electron flow. So the value of a standard reduction potential tells us the tendency of a chemical to gain or lose electrons. So a large positive value means the species is easily reduced and therefore a strong oxidizing agent. So a large negative value means the species is easily oxidized and therefore a strong reducing agent. So remember, a large positive value for the standard reduction, it means that the species or the substance is easily reduced and it is a strong oxidizing agent. However, a large negative value for the standard for the standard uh, for a standard reduction potential, it means that the species or the reaction easily oxidize and therefore it is a good or a strong reducing agent. So metals like sodium or zinc with negative values are strong reducers, while ions like silver or iron with positive values are strong oxidizers. So, like as an example, I presented earlier that the silver ion plus 0.799 volts will pull electrons away from zinc of negative 0.763 volt in a galvanic cell, creating a spontaneous reaction. So for a galvanic cell, the half reaction with the more positive reduction potential will be the cathode. So the cathode is the electrode with the more positive reduction potential, and the anode is the one with the more negative value. So if we calculate the overall cell potential using the equation, so we have here the cell potential is equal to the standard reduction potential for the cathode minus the standard reduction potential for the anode. So this formula helps us determine whether the overall cell reaction is spontaneous if the standard reduction potential is positive, the cell can produce electricity spontaneously. Just like I've mentioned, the zinc copper cell. So if we go on, for example, if we have here the zinc copper cell, we're in the as here previously we have here the zinc is positive zero is negative 0.763 volt, and the copper is positive 0.337 volt. So it means that if you use this formula, the standard reduction potential uh, for any pair of half reaction, for example, for the zinc copper cell, you have here positive 0.337 minus the zinc, which is negative 763 volts. This is volt and volt, which is equal to plus 1.10 volts. So it means that the overall cell reaction for this zinc copper cell is spontaneous. So this figure arranges standard reduction potentials. So from negative, most negative to the most positive. So the elements on the left side, like zinc and copper, like zinc and iron, have negative potentials, meaning they are easily oxidized and act as anodes. So these elements on the right side, like silver and gold, like gold and silver, have positive potentials, meaning they are easily reduced and act as cathodes. So in the example shown, iron is oxidized. Here, iron is oxidized, while copper is reduced. So consistent with their potential in the chart, a simple way to remember: left gives electrons, right receives electrons in a standard potential series. So let's have this problem, example problem 1. Copper and iron, generally in the form of steel, are two of the many metals used in designing machines. Using standard reduction potentials, identify the anode and the cathode, and determine the cell potential for a galvanic cell composed of copper and iron. Assume standard conditions. B, we can also construct a galvanic cell using copper and silver. Confirm that the potential of the following galvanic cell is 0.462 volts. So copper, here, solid copper with a phase change of copper, uh, copper, copper ions in 1 molarity. Then you have here the you have here you have sorry you have here the salt bridge, this one, the salt bridge, then the silver iron in 1 molarity, then you have the phase change into silver. So remember, we have here, so what we're going to do is that to answer this letter A using standard reduction potentials, identify the anode and the cathode, and determine the cell potential for a galvanic galvanic cell composed of copper and iron. So now let's use the table. So from this table, let's go back. Here, you have here the iron and then the copper. So we're going to use this, uh, this standard reduction potential. So let's go back to the problem. Okay. So let's go back to the problem. Let's have another slide. So here. So for letter A, if we're going to use the table, we're going to use the table based on the slide. So here we have, it says here, the problem says copper and iron. So we have here iron in aqueous solution. It's 2 electrons will form into iron solid, and it has a cell potential which is equals to negative 0.44 volts. Then for the copper aqueous solution, plus 2 electrons will form into copper solid, where in the cell potential is 0.337 volts. Iron, it means here the iron must be oxidized for a combination of these two half reactions to yield a positive potential, a cell potential. So here, if you go back here, it means that you have the overall reaction here. Since iron is the oxidation, is since you have here iron must be oxidized for a combination of these two half reactions. So it means that this iron, it means the iron is the anode. It is being oxidized. So it means that iron solid will form into iron ions in aqueous solution plus the 2 electrons. So in here, if you're going to look at it, the anode by the values, the anode here is the iron, while the cathode here is the copper. So now, because the copper is being reduced, it's positive, while the iron is oxidized. So here you have, for example, if you go back here, so it means copper plus 2 electrons will form into copper solid. So the value here is, it means that cancel and then cancel. So it means here the final overall reaction is iron solid plus copper ions in aqueous solution will form into iron ions in aqueous solution plus copper solid. So what is being asked here is the no. What is being asked here is the cell potential, which is equal to the cell potential for reduction minus the oxidation. So let's have another slide here. So if you have here is equal to reduction minus the oxidation. So let's go back here. So it means that, however, you must always remember that the value here still stays the same, which is negative, even though this has been transformed, unlike the previously, the one that we talk about on this stoichiometry. So here, what happens here now is that is equal, the reduction here is 0.337 volts minus the oxidation, which is the iron, is negative 0.44 volts. Therefore, the cell potential here is equal to 0.78 volts. So 0.78 or 7, sorry, 7, 7, 7, or 0.78 volts. So copper here is the cathode in the cell because copper is reduced, while the iron is the anode because it is oxidized. So another question is, we can also assume standard conditions. We can also construct a galvanic cell using copper and silver. Confirms the potential of the following galvanic cell is 0.462. So now, let's go to letter B. Letter B. So find the two, we have based on the slides, based on the table. Let's go back to the table. We have here, it says here, let's go back here. It says copper, copper solid, base change of copper ions. Then there, salt bridge. Then, sorry, because there is, the standard is in molarity. 1 molar for the aqueous solution. So sorry. Okay. So here you have 1 molarity, then the salt bridge. Then here you have here silver ion, then 1 molarity. Then you have the phase change into silver salt. So now let's go to the table again. Let's go to the table where what are the values that we're going to use. So we have here silver, and then we have also the copper. So if we're going to identify here, we're going to identify here which one is the cathode and which one is the anode. So the cathode here, based on the values, the cathode here based on uh, the cathode here based on the values is the silver because it has a higher standard reduction potential compared with the copper. So now let's go back to the problem. So now let's go back to the problem. So if we equate this one into two half reactions, we have here silver ion in aqueous solution plus one electron, it will lose one electron, lose what? It will form into silver solid. Then for the copper ions, then aqueous solution, then it has two electrons, then it will form into copper solid. So the cell potential for the silver and copper, let's go back to the values that based on the table. You have here silver plus 0.7994 and the copper is plus 0.337. Okay, so here is the silver is 0.7994 volts and the copper is 0.337 volts. So from these values, we can already identify, as I've mentioned, that copper is oxidized, while the while silver is being is reduced. So therefore, copper is the anode, while copper is the anode, while silver is the cathode. So we will be able, so is the cathode. So if you will look at if you'll do with the formula, so it means that the silver, it means that the silver will reduce electrons, will reduce will reduce electrons, while this we lose electrons while the copper will gain electrons. So here it means silver will is here that since copper will gain electrons, so this equation will become copper solid will form into copper ions in aqueous solution plus 2 electrons. So since copper is oxidized and copper is the anode, so it will have it will become this equation. So now if we connect this both of this equation, this one and this two equation, what happens now is that it will become here, it means copper solid plus silver aqueous solution plus, no, there's no more electrons here. This is not balanced. Sorry, because there are two electrons here, two electrons. So what happens is that, let me correct this one. So this one will become 2, sorry. This will become 2 in order to balance the equation we have here. So it means that there are here 2, because this one is canceled and this one is canceled. So it will form into copper ion sorry. Again, copper ion in aqueous solution plus here to solid. So therefore, if we equate this one to the cell potential of the reaction, it means reduction minus reaction cell potential you have here. You'll be able to here identify already that 0.7 reduction 994 minus in volts minus 0.337 volts, which is equal to 0.462 volts. So, so in this clearly explains that the copper is oxidized and the silver is reduced. So the cell potential for this reaction is equal to 0.462 volts. So that ends our part one for the electrochemistry. And I will do another part of for the part two of our electrochemistry. So hope you understand and thank you very much for listening and please take notes on everything what I've said. Okay, thank you, mechanical engineering students, and I will do another part for this topic.